Welcome back, students. Today we're going to do rough sketches of titration curves. Okay, so you remember what a titration is from last year. You have a long skinny tube called a burette, squirting drops of liquid into a flask. The sample is usually the thing we're trying to find the concentration of, but that's the sample, and what in there is called the titrant. And the most important thing I want to say here is when you read a question, you got to figure out what substance is in the burette, the titrant, and what substance is the sample in the flask. The rule is the substance being titrated is in the flask. Okay, so I'm going to do a strong titration. So this is the titration of HCl. The substance being titrated, HCl, is in the flask, being titrated with sodium hydroxide. Strong acid with strong base. Okay, I'm going to label the bottom of the graph the volume of sodium hydroxide that we add to the hydrochloric acid. That's one way to show our reaction, Bronsted-Lowry. Okay, now, if I was to take the pH of the acid right now, I just found some picture on the internet, but the pH of hydrochloric acid is 1, right? So it would be a pH of 1. So this graph starts quite low when we're measuring pH. We want to draw how would the pH change as I squirt base in to acid, okay? So the pH is around 1. Okay, now I start squirting acid in. You would think that we just get this straight line, this diagonal line all the way up to 13, but it actually doesn't do that. It is going to do this. Now you'd think you'd have this just nice sloping diagonal line, but that's actually what happens. Okay, so whenever you have a sharp vertical on a graph like this, it's called a quantitative reaction, which means 100% reaction. This does not have buffering, so I'll explain buffering in a little bit. Strong curves are not buffers. And the equivalence point is the middle of the vertical, which in this case, because you have a strong acid at 1 ending at a strong base of 13, is right in the middle around 7. Okay, so that's important for how we compare these. Okay, let's do a strong-weak combination. So let's say we're titrating acetic acid with sodium hydroxide. The substance being titrated is in the flask. Sodium hydroxide's up there. Now I'm going to add sodium hydroxide to this weak acid. So CH3COH is reacting with each hydroxide drop that falls into the flask. Now the graph looks basically the same, except you're starting higher. You're starting at 3 or around there. This is just a rough sketch, so it doesn't have to be exact, because acetic acid is a weak acid. Okay, so you're not at 1, you're higher. Okay, there was a quantitative reaction because we have a sharp vertical. So that's why you only see an arrow, not an equilibrium arrow, a backwards arrow. This reaction formed a 100% reaction because we had this strong base with this weak acid, and by nature this reaction is 100%. Okay, we do have buffering. Buffering is formed when we have a weak acid and its negative ion present at the same time, and buffering resists a change in pH. In the next lesson I'll show you a little bit more about buffers. Buffering occurs before the equivalence point, not after. And the equivalence point won't be at 7. It will be shifted a little higher than 7 because the line, the vertical, has moved up a bit because we started higher. So the rule is the equivalence point shifts towards the stronger substance. We've got weak acid at the bottom, strong base at the top. Equivalence point, when compared to 7, has shifted a little higher. It's shifted towards the stronger substance. Okay, equilibrium shifts towards the stronger substance. So it's a little higher than 7. Okay, a weak graph would look something like this. It's kind of gradual. There's no quantitative sharp vertical there. You can't really determine an equivalence point. There is buffering because you have weak acids, and by definition, buffering contains weak acid. But you're not going to get tested on these weak ones, but that's what they look like for comparison purposes. Okay, you can also have polyprotic substances like H2CO3, and it being titrated here, has 2 H's. It's got 2 protons. So it actually is going to do this. So if I pick my strongest acid, there's my strongest base. First reaction, H2CO3 throws away a proton and makes HCO3 negative. And then HCO3 negative throws away another proton and turns into CO3 negative. So I cancel those out because they're on both sides. And H2CO3 has reacted with 2 hydroxides, which means we have 2 verticals in the graph. 2 protons, 2 verticals. Okay, which means we also have 2 equivalence points and 2 buffering regions. Okay, so if you have something that's polyprotic, which has 2 protons, or polybasic, can grab 2 protons or more, that's what your titration curves are going to look like. Either going up or down, they're going to have more than 1 vertical. Indicators. So if this is our titration, if this is our reaction, we have these indicators on page 10 in your data book. Bromothymol blue is blue, I think at 7.6, and from 6.0 and down, it's yellow. So in this titration, because the line is going up, we would have yellow in the flask, and then it would turn to blue. Okay, so if I put my indicator in there, it would be yellow because acetic acid starting at like a pH of 3, it would be yellow. And as I did my titration, it would turn blue. Okay. Now, a classic test question they ask is, out of the following, which would be the best indicator? The best indicator, oops, let me back that up. The best indicator is the one that is closest to the equivalence point. So the 135 benzene one, that's too high. It's off the vertical. That one doesn't count. Orange 4 is below. That doesn't count. The other 3, bromo green, bromo blue, and phenolphthalein, are actually all good indicators. They would work for this reaction. But the very best one is bromothymol blue because it's the one that's closest to the equivalence point. And I think this page is just showing what happens when I do a titration. Yeah, I'm just running out of acid. Every time base comes in, I'm killing acid, killing acid, killing acid. And my graph has gone to that point, my titration curve, I should say. And then I do one more drop, and that base lingers, changes and like that 1 or 2 drops makes that happen. Like that whole line happens with 1 or 2 drops. That's why it's turned blue now, because we're now above the blue point of that indicator. Then as I keep adding in base, my titration finishes off. Now base is just piling up, pH of 13, and there we go. Okay? All right, that's it for that lesson. Thank you for watching. Good luck.